nice. I know there are some people that are still arriving tomorrow. So I guess we're going to have a group, let's say a photo. We're going to make a group photo tomorrow, right? I'll give you more instructions about it. And so, well, I have the pleasure here of introducing you to Fernando Brandão. So he's a very well-known scientist in quantum information. He's now officially at Caltech, but at the moment spending some time at Google Artificial Intelligence Laboratory. And before he spent in Microsoft, in UCL in London, and he did his PhD with Martin Plenier in London also, right? And he's Brazilian from Belo Horizonte, and so we're very happy to have him here. I'll introduce you later to Burak when it comes his time. So we will have the first lecture by Fernando, and after the coffee break, Burak will take over, okay? So I pass the word to Fernando now, and enjoy it, okay?
Okay, thank you. Is it on? I guess so. So, welcome everyone. Thank you for coming. Or it's not. It is on, no? Okay. But can you? Right. So it's. Oh no. Yeah. Now I can hear myself too. So it's good to be here. It's always good to come to Brazil. So how many of you speak Portuguese? Raise your hands. So how many don't speak Portuguese? Okay, good. Yeah. Right. So I started studying quantum information, quantum computing here in Brazil many years ago, like 30 years ago, and then I have been doing that since then. I think it's a really interesting area for doing research, and there has been a lot of developments in the last decades, even before, of course. But it feels like things are speeding up. Has been speeding up for 10 years, and even more now. So I think it's a good time to do research in the area, and that hope to convey this impression to you in this course. So I have a plan, but it's not like set on stone. So if you feel free to ask as many questions as you want during the talk, and if I'm going too slow, also just let me know. But it's really going to be a dialogue between I and me and you. So yeah, just stop me whenever you want. One title for the course could be Entanglement Frontier, right? So it's different from the one I said before, but it could be this one. And one way to see that is that, well, I'm going to tell you what entanglement is if you don't know yet, right, soon. But for now, just think about it will be some special kind of correlations that exist only in quantum mechanics. When you have very small systems, electrons or ions, photons and so on, they can be correlated two or more systems in a way which there is no classical analog, so in classical mechanics. And this is a very rich phenomenon in quantum physics. It leads to potential technological applications that we're going to view only briefly, and that's the motivation for studying entanglement in quantum computing. But it's also just people are realizing more and more a very fundamental physical quantity, and therefore the influence of entanglement in general is just growing and growing. That's maybe the main point of this lecture. So in physics, there is like, you can call some frontiers of physics, right? So like which directions there is research nowadays in physics, right? So you could consider maybe, let's look at 3. So for example, if you go to short distances, right? So we can go very small distance, then we have quantum mechanics, of course, right? But then we can go even smaller distance, or even like smaller distance and high energy, and then we go to quantum field theory, right? So a few years ago, we had the discovery of the Higgs boson. There was a great accomplishment for very small distances, right? So it was a very good indication that the standard model of particle physics is correct. So, but then we would like to go even further. We'd like to go to high energy, smaller distances. For example, probing quantum gravity, or seeing if string theory is correct, and so on, right? So that's one direction that is very fruitful in physics. We can also go the other way and look at very long distances, right? So that's, for example, I don't know, maybe you want to study the cosmic microwave background, or you want to understand what is dark matter, right? Or like understand better black holes and so on, right? So that's also an exciting direction, like in terms of cosmology and astrophysics. So these are more traditional, right? Like frontiers of physics. We definitely understand the short and long distances. Entanglement and quantum computing generally, I think our way to see what we are doing is that we're exploring another frontier of physics, but of maybe we can call the complexity frontier, right? So what we want to do is not to consider extremely small quantum systems or quantum systems of very high energy, and neither very big ones, right, where gravity, for example, is relevant, but ones where we control them very well, and we control a lot of them, right? So we don't want to just study one quantum system, we want to understand millions of them, but maybe a little bit different from here. We want to understand millions of them with full control over them, right? So, and that's how the idea of like quantum computation appears, right? So, and then, well, there is, that's not a completely new direction, so you can say, well, in condensed matter physics, people have been doing that for a long time, right? So there is this sentence, maybe to Philip Anderson, say, more is different. And it's this idea of emergency, right? So even though we can, we know quantum mechanics, so we understand, so suppose there's no relativistic effect, so we understand quantum mechanics very well. For 100 years, we have been testing it, and it seems to be the correct theory at the microscopic level. So if you just have one quantum system, there is no question, right? If you do an experiment, we know what we're going to get, right? For sure. But then if you have a lot of quantum systems, you have thousands of them, even though we know the fundamental laws, doesn't mean that we understand what's going on there, right? Just because, there is, we have the underlying dynamics, we understand them well, but it just becomes very complex to predict what the system of 1,000 particles will do. And moreover, it can be very different from what we expect just from the fundamentals of quantum mechanics, right? So there is the idea of emergent complexity. There is for all science, of course, right? So, like everything in the end is just quantum mechanics if you want, right? But if you want to study psychology, we're not going to use the laws of quantum mechanics, right? So there's all these levels. But what we want to do here, what is different from what had been done before, we want to do that in a systematic way, right? And we want to take to the extreme. Say what is the most complex quantum system that we can build, and what it can do for us. And the key distinction of asking this question in the quantum case to the classical case is entanglement, right? And that will be one of the points that I want to make to you. Okay, so just. So I haven't told you what it is yet, right? But there is this thing, which, as I mentioned, is these correlations between quantum systems. And, well, the first one to talk about entanglement was Schrödinger a long time ago, right? He gave the name, actually. And just realized that you could write the wave function of two particles in this particular way that we're going to write down soon, which he found it was a bit peculiar. He didn't know what to get from there, right? Then people just didn't care about it, right? They were very excited about applying quantum mechanics to all kinds of situations and getting all these great predictions to experiment. Then some decades later came along Einstein, and he was very unhappy about some of the characteristics of entanglement, maybe more from a philosophical point of view or from a direction of fundamentals of quantum mechanics, but he didn't like it. He thought that the existence of this kind of correlations indicated that there was something missing in the theory. But then people didn't care so much again, right? They were busy doing other stuff. Then there was Bell came along and he refuted Einstein in a way. He saw that this completion of quantum theory that Einstein wanted to understand entanglement couldn't happen. He kind of gave a very easy argument how basically you have to accept these features of quantum mechanics. We are going to see them, which they might not be so satisfying from the first view, but they're just the way the theory works. But again, there wasn't a big splash, right? So nowadays people really like it, but there wasn't back then. I think the moment that where people really start studying entanglements and being excited about it, what people start looking at what quantum mechanics could do in terms of computation or information processing, right? And this came with quantum computing and quantum information science, like around 25 years ago, that really kicked off. So what is the idea? The idea is that looking at entanglements, so looking at these special kinds of correlations that quantum mechanical systems can have, you can do stuff in terms of like technology that you cannot do just using normal classical mechanics, right? And that's exciting one day if you can implement this, right? So there is this idea of quantum computation, right? So what you want to do here, you just have a lot of quantum systems. For example, a system of many photons or of many superconducting qubits, whatever you want. And you want to control them really well, and then you just want to perform some computation using them, right? So you just, each time choose two of them, you implement some Hamiltonian on them in a control way, then choose another two of them and so on. And then you want to build a complicated quantum evolution out of these basic evolutions. And moreover, you want to try to see whether you can use that in the same way the classical computing is used to solve some problems. And maybe there is a speed up here, right? Maybe there is an advantage here. And people found out that there is advantage for some problems, and that's exciting, right? And as we are going to see, entanglement kind of plays a role here, right? So basically, without entanglement, we couldn't have this new kind of computation, right? So that's one of the points I want to make. Then of course, here people, people study quantum algorithms, right? Basically, once you have this special kind of computer, which problems can you solve on them, right? And then that's an interesting area. Try to come up with applications for quantum mechanics computationally. And then people also study what you can call quantum complexity. Not to mistake by the other complexities like quantum complexity theory, in the sense of a quantum analog of classical complexity theory. Basically, we want to understand the limitations of quantum computer, right? So it's not a quantum computer can solve any problem much faster than classical computing. It's very subtle which problems it can have advantage over classical computing. I'm going to mention some of them later. But we also understand limitations, and there are many limitations. This is what we study, right? So then in another direction, interesting way of seeing entanglement is that it's some kind of correlations which can be as strong as possible between two particles, but which are in a sense independent of anything else. So we call them like monogamous correlations, and we're going to quantify that later. But there is this feature of entanglement which is very special, and what this allows us to do is what we call a quantum key distribution. So that's a way of establishing a secret key between Alice and Bob, which is secure, it's completely secure. No one knows else. No one else knows. And the security is unconditional. It's based on the laws of physics. If quantum mechanics is correct, this has to work. And that's unlike what we have in classical mechanics, right? In classical mechanics, there is no way to establish key in this way. So we need some, for example, computational assumption or Alice and Bob have to come together and then separate and so on. So that's also some new thing that we could do. And actually, this has been implemented, right? There is people selling quantum key distribution devices. So you can buy them if you want. It's very expensive, but not very useful. But well, and not very useful yet because, right, we need some way to distribute quantum systems here. But this is the reality, right? So then there is some other ones. Let me just go quickly. People start studying how to use, entanglement and how to use quantum particles to do communication. So this is quantum communication. And again, there are interesting things, like we're going to see later, teleportation. That's an interesting protocol in quantum communication using entanglement. So, right, also the way we think about how to send information down some channel or some wire, it has to change if you look at quantum mechanics and entanglements. Then, if you want to do metrology, basically you want to measure some physical quantity to high precision, for example, some frequency. There is some limits, fundamental limits to what you can do. If you have entanglement, you can beat these limits and do better, right? So that would be another application. And finally, there is one area that will also be important for us here and was done, right? So this, maybe we could write this is like the view of quantum information science. And finally, as we're going to see too, Entanglement is very nice, but it's very fragile too, right? And that's why we don't observe us in our everyday world. So if you want to one day build quantum computation or even do quantum key distribution over very large distance and so on, we need some form of protecting these very fragile quantum correlations, right? And luckily there is a way of doing that. It's not easy to implement, but there is a way to do that. That's quantum error correction. And interesting, quantum error correction also uses entanglement, right? So, this is, you can see as a way of protecting some useful entanglement like that is used for computation or for quantum key distribution. But the way to do this quantum error correction, to protect it, is to encode the quantum information in some very non-local way using entanglement again, right? And that's, and we're going to see that later, how that's done exactly. But, this will be maybe like some of the biggest areas of quantum information science. They all have this view of entanglement as some useful resource, right? So you want to use it. Maybe you don't care so much about the fundamental implications or about the physical properties, but you care it because once you have it in a control way, you can do stuff with it, right? You can do key distribution or computation and so on, right? So there was this very pragmatic view of entanglement before, and this was the main interest of entanglement for a long time, right? So definitely when I started studying it, this was the prevailing view, right? So it was something that people in quantum information were very excited about, but not in other areas of physics, right? They thought maybe it was engineering or it was maybe interesting math, but not really physics, not really traditional physics, right? But this changed, and changed quite dramatically in my opinion. So now, many people in different areas of physics that I talk about, they're really excited about entanglement in a way that surprises me. And this is what we want to do in this talk, right? So what we want to do is, again, look at entanglement, but now connect to other areas of modern physics, right? So there's a lot to say here, and we won't have time to do it, to tell everything, so I'll just choose a few topics and tell you, and Burak will do the same. But for example, you can look at condensed matter physics. And then there's a very beautiful connection of entanglements, and moreover this tight relationship of entanglement and quantum error correction codes with topological order. So what is topological order? Well, that's just, the way we like to classify phase of matters is just by looking at some symmetry group, right? If the symmetry is broken or not, right? So we can classify phase transition from a liquid to a solid by that, right? So translation invariance, translation symmetry in that case is broken when you go to the solids. And there was, you can classify most phases using that paradigm, but not all of them. So there is some phases, and this is what we call, there is topological order, for which there is no local order parameter there, and you need to understand in a different way, okay? And what eventually was found out, for example, the fractional quantum Hall effect is an example of state of topological order, and there are others. Or spin liquids. Then what eventually was realized is that actually the way to understand them is to look at the structure of entanglement in their low energy states. We are going to see that in more detail later. And then looking at this connection, this gives a much nicer view. And moreover, it's very related to quantum error correcting codes too, right? So, there is this concept here, right? Quantum error correcting code is really looks like an engineering concept, right? Or at least something very artificial that we can come up to try to use quantum systems in a very different regime where they exist in nature. But then you see a concept which just connects to it very naturally, and some of the systems, they are just there, right? We can just, nature just realized this. So this was one of the first examples, and it was a surprise. But then it's just growing, right? So there is like people start using entanglement to understand phase transitions more generally. like critical systems, and moreover, to study numerical methods here. So it turns out that the amount of entanglement in the system, as we are going to quantify later, has a direct influence on how easy it is to simulate the system classically, numerically, right? And therefore, once we understand entanglement better, we can come up with better methods to simulate them classically, and even sometimes with some better analytical tools to understand these many-body strongly correlated systems. And that will be the main point of what Burak is going to tell you, right? So his lectures will be based on this problem, how to, once we understand entanglements, we can come up with new tools to understand strongly correlated systems, for example, using tensor networks, and how we can understand them better in this way. Then another area where there's some nice emerging connections is in statistical mechanics and thermodynamics. So one example is a recent one. People are interested again in quantum chaos after, right? There was a lot of interest maybe in the 70s, the 80s, then it died off. Now there is a resurgence. And their interest, but now in a different way, now really quantum chaos of many-body systems and try to understand them better. And they're interested also because now they found the antagonist of quantum chaos, which is many-body localization. That's a system, again, is the same as a localized system that Anderson found out many decades ago, but in the strongly interacting case. So it's an interesting system to study. And there's transitions between these two phases and so on. So it turns out that the entanglement is very useful to understand these two phases. And we are going to see that maybe in a few lectures. But there is maybe these two phases of statistical mechanics. That's the way we understand it now. And the way to understand their differences and how to describe them and so on, we have to look at the entanglement properties in the two cases. Then there are other examples, and another one maybe is if you want to understand thermodynamics at small scale. Then you can say, well, thermodynamics, you really need these very big systems, right? And like the way Carnot was seeing them, where we can do some coarse graining and we only care about a few variables like temperature and energy and so on. But it turns out what we learned recently is that not really the case. So even if you go at a few quantum particles, a lot of thermodynamics still carries over there, right? And it still works there. There is some modifications, but it still works there. And here, okay, of course, entanglement plays a role there because, right, it exists as a dynamic scale. We have to understand it. But it's more than that. A lot of the tools that we developed to study entanglements, they turns out just to be the right tools here to understand thermodynamics at a small scale, right? And that's, I think, an interesting direction. We'll tell more later. Sorry for a lot of things, but I think if it's too much for you now, just have in your mind that entanglement became a very rich concept in physics, right, with a lot of applications. And therefore, once you do this course and you suffer for the 5 days, right, you'll be in a good position to attack any of these problems that you want, right? And then you can choose which one you like the most. Then in high energy physics, also growing, maybe a little bit of cosmology. So first, one example where it starts playing a very important role is in trying to understand better black holes. Right, so we know black holes are very interesting because it's one of the few places where we might be able to see effects of quantum gravity on a bigger scale. So this is like a clue if you want to understand quantum gravity better, that we, at least most of us don't yet, right? But also just poses some very interesting questions from a pure quantum mechanical point of view, and there is a lot of debates about these black holes, right, and their properties for many decades now. And very recently there was a renewed interest in black holes. People, there are some problems about black holes whether quantum information can be copied or not. That we know they shouldn't be the case if unitarity is preserved there and so on. I'm going to review some of them, not in a lot of details. But very recently, some people found puts this like this question we have about black holes that we don't really understand yet on a much better footing using entanglements and seeing how things that people believe was true before about unitarity of black holes or effective quantum field theory being true at the horizon and so on, how they are incompatible with some properties of entanglement that we know to be true. So we're going to see that. I think that's interesting. And even, I guess, more recently, in quantum gravity or in string theory, actually, or more specific in this ADS-CFT correspondence. Entanglement is starting to have a big influence too, right? So for those of you who haven't heard of this is just a connection that was done by Romualdo Assina maybe 20 years ago, or maybe more, so he conjectured the correspondence of a theory of quantum gravity in ADS space, so with negative cosmological constants. So basically quantum gravity in a box, and saying that this theory of quantum gravity in D+1 dimension, in D+1 dimension, was equivalent in a way to a pure quantum field theory on the boundary in D dimensions, and to a conformal field theory on the boundary. Okay, and I mean, there's no proofs and so on, but there's a lot of things suggesting that that's the case indeed. But there was a lot of characteristics of this correspondence that seems very mysterious, and many are still mysterious. But some of them people start using methods from entanglement from quantum information theory recently, and they made a lot of progress. They became much clearer later, for example, especially like using quantum error correction again. And I think that's a exciting new direction, right? So connecting these two topics. And I'll mention a little bit about this, but I think Burak will cover this in his last lecture in more detail. So, and of course, it's not the topic of this course because I'm a theorist, and I would be a terrible experimentalist. At least when I did experimental physics, it seems to be the case. But there is experimental physics, right? We shouldn't forget that it exists. And there, the influence is huge, right? So, and why it's huge? Well, it's huge because they say, okay, we want to really control this on a very high level, right, with the large numbers of particles possible. And that's very challenging, but that motivates, right, a lot of great experiments, right? So there is people looking, for example, at superconducting qubits. So these are like engineered two-level quantum systems. The way to think about them, for example, is that you have two superconducting islands, and you put a Josephson junction in the middle. Then Cooper pairs can tunnel from one island to the other, right? But then there's these two condensates of Cooper pairs, and there is like two conjugate quantum variables, like the number of excitations and the phase. And this is the same as you should think, same as X and P. So this can define a two-level quantum system in this way. That's the qubits. And the nice thing is that they're pretty big qubits. These are really on the level of micrometers, right? The size of like this junction and the islands. So it's very easy to address them. And people can get now them with very good coherence time. So the qubits, they don't interact much with the environment. So these people start scaling this up, right? So there's experiments with 30 qubits, there soon be with 72 qubits, but they have very good coherence properties. And that's a great place to start seeing entanglement on a larger scale and all the stuff that we can do with entanglement. So ion traps, the same. You can put a bunch of ions maybe in a linear trap using electromagnetic waves or in a two-dimensional array and so on. And they will couple because they're ions, right? The emotional state is coupled, so they can, you can engineer interactions between them. And this can be done in a control way and larger systems again, and so on, right? And there are many more. They're like topological qubits, there is photonics, and so on. So there is like this race of seeing what is the most suitable physical system to scale up, right? To have entanglement between a lot of particles, and then eventually to build a quantum computer. And of course, this leads to a lot of interesting questions in experimental physics, but also to a lot of progress, right? And there is more to come, right? So I think we're really in this interesting regime where this, for a long time, the theory was very disconnected to the experiments in quantum computing. Now I think they're coming together, and this will happen more and more in the future. So that's the view, right? So I think that's maybe why you should care about entanglement, why it's an interesting concept. But I haven't told you what it is yet, right? So let's get to there now. Let's put some equations now. Is there any question on this, more of an introduction or anything that I didn't mention that you would like to add up? Or? Okay. Right. So, how many of you know quantum mechanics? Everyone, right? Okay, good. But anyway, I'm going to review it very quickly first. Okay, maybe just more for notation, but it'll be. But I guess it's fair to say that if you didn't know before, you're not going to learn it now. But okay, so quantum mechanics, right? So we are going to consider two kinds of states in quantum mechanics. One is called pure states. So pure state is the traditional state that you see, right, when you first learn quantum mechanics. I'm going to use Dirac notation, so ket psi. So a nice thing about quantum information and entanglements is that almost everything of interest we can study with qubits, basically two-level systems, or at least with finite dimensional systems, okay? And I'm going to do this in this course. Because we don't lose much, and it becomes things much simpler, so a quantum state for me will be just a pure state, will be a d-dimensional vector, right, in a d-dimensional complex vector space, okay? Of unit norm, right? So the norm has to be, the Euclidean norm is 1. And what I mentioned before is just the case when d equals 2, that's just what we call qubits, right? Is the quantum mechanical analog of a bit, has two states. Right, how can you write the most general one? You just choose a basis, maybe the 0, 1 basis, right? And that would be the states, where alpha and beta are two coefficients. So they say it has to be normalized, so the square or the absolute values has to be equal to 1. So what is this basis? Well, it just has, we can choose any two orthogonal vectors we want in this two-dimensional vector space. So a good choice is just to choose the canonical basis. So 0, I mean, this is the notation, right? Ket 0 means this 1, 0 vector. Ket 1, 0, 1. Okay, so that's the first state we learn in quantum mechanics, and actually in a way that's the most fundamental in the sense that if you wanted, you could explain everything in quantum mechanics just using this kind of states. But it's very convenient to have a more general class of states, which we call mixed states, that we're going to use. So let me introduce them too. So here now, instead of a vector in a complex vector space, we have what we call a density matrix. Is a matrix now, and this lives in the set of density matrix over the vector space CD. So this is, in words, is a D by D positive semi-definite matrix of trace 1, of unit trace. Right, so meaning rho has to be Hermitian. All the eigenvalues of rho have to be bigger or equal than 0. And the sum of the eigenvalues, which is the trace, has to be equal to 1. Okay? Now because of that, you can write any density matrix that you want. You can always think of a density matrix as a convex combination. Pi is a probability distribution. As a convex combination of pure states. But now it's a matrix, right? So if you want to make a matrix, if you want to make a matrix out of a vector, what we should do? Well, we just take the outer products of the vector with itself. So this would be like the pure state representation of the vector psi I in terms of a density matrix, right? So this is, the name for that is a density matrix. And you can also think of density matrix just as, we have a particular pure state, but we don't know which one we have. We have some classical ignorance about the pure state that we have, and therefore we have to look at this average, right? That's one interpretation. There is a different one, which comes from, actually from entanglement, but this one I'm going to tell you like in 5 minutes because I have to introduce something else before. Okay. Then we can look at, in terms of states, that's almost everything we need. We need something else. We have to understand how we compose two states. So suppose we have two physical systems. Each one, right, has a quantum state of itself, of course, but now we want a quantum state of the composite system, right? So how we do? And this we do, right, using the tensor product, right? So suppose we have two quantum systems, system AB, and then again, right, so what is, given a quantum state, we have to specify in which vector space it lives, but it's a vector space just because I talk about finite dimensional systems, but in general it would be like a Hilbert space associated to it, right? So because of that, sometimes we call there's the systems and then the corresponding spaces. Let's denote them HA and HB, right? And for us, this can be really, you can just think of them as some isomorphic space to a finite dimensional complex vector space of dimension dA and another one dimension dB. Okay. Then composite system. Then the Hilbert space. Of the composite system. Less than only by HAB. This will be given by the tensor product of the two vector spaces. Okay, so this is the tensor product. So how many of you have seen the tensor product before? Okay, great. So almost everyone. All right. So what does this mean? So it means that let's take an example now in terms of states, right? So suppose we have state psi A, right, for the first particle, and some phi B for the second particle. Now the joint states is given by this one, okay? And now, what is the, maybe, yes? Or this, the whole thing I should use? Half. Oh, half, okay, good, yeah. All right. And this is, probably have seen before as well, but let me just remind you, there is a specific, no, this is a well-defined mathematical operation, right? What this means, if psi has components psi 1 at psi dA, right? And yes.
What do you actually mean by a joint state?
I mean a quantum state which describes all the physical properties of the two particles.
Do you mean you have two quantum systems which are physically close to one another?
Or they can be far away, but we wanna a quantum. Well, I haven't put dynamics yet, right? So at the moment, I'm just describing states. So I just say, okay, I want to have a quantum mechanical description of an electron here, an electron in the moon, right? So there is a way to do that, right? And that's using a quantum state of the two particles, right? So maybe that case is boring. Well, a part is electron, so they will be antisymmetric, but it's boring because they're not interacting, right? But still you can have a joint description of them, right? But I'm going to talk about dynamics very soon. So then, yeah. But you know, if this, right, the nice thing about finite dimension, they are vectors, right? So everything is very concrete, right? So what is this state in that case? So what is the rule of tensor product? You just, first this vector now, this is a vector, this guy acts on, right, well, the dimension of this, right, so the dimension of this guy is on, this acts on a dA times dB vector space, right? So the dimensions get multiplied, right, and that will be important, right? So dA times dB dimensional vector space. And the way we do that is that we just first pad a bunch of vectors. The first one is psi1 multiplied by this vector. So this will be like the first component psi1, phi1, then psi1, phi2, and so on, up to psi1, phi dA, okay? Then we multiply the second component of this by the second vector again. Then it's psi2, phi1, psi2, phi2, and so on, up to multiplying the last element of this by the vector again, right? So the last thing will be psi dA phi1 up to psi dA phi dB. Okay, so you can check, of course, this has dA times dB components, right? And that's the way we define it. Okay, but now you can ask, right? Great, so is that the most general quantum state you can have? And the answer is not, because quantum mechanics is linear, right? So whenever we have any state, any set of states of this form, we can take linear combinations of them, right? We can take superpositions of them, and that's a valid quantum state as well, right? So, so you can have, you know, the most general states, psi AB, on this vector space. How can you write it? Well, what you do is just choose basis for the two vector spaces. And just use quantum mechanics, right, the linearity principle, right? So, okay, so you write like this. So that's the most general quantum state of this composite system. Think about like state of two electrons or two photons or whatever two quantum systems you want. But now we see something interesting already, I think, which is that in general, there doesn't exist local pure states. So states, let's call them eta A and nu B, such that psi B is the tensor product of the two states. Okay, so what is an example of this? So most states of a composite system, they will not be able to be written, they cannot be written as this tensor product of two pure local states. So one example of that is, suppose we have two qubits. Now a state, so we call this phi plus state. You know, to save time, instead of writing tensor product every time, I just write 0, 0. But that means 0 tensor product 0 on B, and 1, 1. Okay. So I give you, I will give you a bunch of calculations to do during the course, and you should try to do them. They are usually they're pretty easy, but it's good to make sure that you're keeping track of what's happening. So the first one I ask you to do is just to prove this, okay? That this state, this particular state, cannot be written like that. Doesn't matter how you choose eta and nu, okay? That's true, but you're going to check it. So what this means? This means that, remember that I said, okay, the most general description in quantum mechanics is these pure states, right? In principle, you could describe everything using pure states, but now I just gave you an example where there is a state of two particles, right? But if you just look at the properties of the first particle, there is no way to describe it by a pure state, right? So there is a pure state description of the composite system, but there is not a pure state description of one of the systems, right? So, and whenever this happens, that's exactly, well, it's a little more subtle, but to first approximation, that's exactly what entanglement is, okay? So now we can already give our definition of entanglement, at least for pure states. For mixed states, we can say something else. What's the question? Yes?
So that state is the pure state in the HID space.
That's right.
Can also be written as a combination of pure states of H, A, and B.
Yeah, that's right. That's right. Yeah. You try to prove that yourself. So what is entanglement? So the way we define entanglement is by what is not first. So we say psi AB. We just do that again. It's just a definition of psi AB. We say is a product state if there exist local states, right? Just like that. At the A, new B, such that this can be written, right? Sorry. As a tensor product, okay? And then two cases. Psi B is entangled. If it's not product. Okay? So that's the first time we see entanglement specifically what it is. So you can see there is some, I haven't told you about measurements yet, but you can already see, probably right from what you know before, quantum mechanics, that indeed, right, this is about correlations on quantum systems, right? So if quantum system can be written in this form, if it's product, right? So the any measurement that we make on A, any prediction that we try to make on A is completely independent, right, of any measurement that we do on B. But if they are not in this way, then there will be correlations between measurements on A and B, right? Now you can say, okay, great, that's just correlations, right? So, two coins which are correlated, we have the same properties again, right? So what is the distinction of entanglement and classical correlations? We'll see later that there is, but just from the definition a priori is not, right, is not clear. Okay, good. Then before, still in states, reduced. Let me introduce another concept, which is the concept of a reduced density matrix. We're also going to use it. What is the idea here? The idea is that we have a quantum state. It can be a pure quantum state of the composite system or mix, right? So I didn't specify, but it's the same, right? Once we have pure states in some vector space, we can form a mixed state as well, just by taking convex combinations of them. So suppose we have this guy, and we're only interested in properties of the A system, for example, okay? So we want to have a mapping from rho AB to just some state that we call rho A, such that this is again a density matrix, and if you only care about properties of A system, it's all encoded here, okay? And what is the right way to do that? Well, the right way is to do an operation that we call partial trace. So, if this was a probability distribution, what we would do, we would just average out, right, the random variable on B. We just take some partial sum over all possible values of B. Here we do the same, but because it's quantum mechanics, we have just to take the trace, but only over the degrees of freedom on B, right? So the way we do that is just we choose any base we want for B. Okay. So this is a basis for B. Well, maybe I should write that. where we do nothing on A, is the identity on A. This is the identity operator. We apply some bra I on B, row AB. Same operation here. Okay. Now we can take, yes.
The second tensor product, you're looking to IB to IA, tensor product, little IB, the second tensor product.
This?
The other one.
Uh-huh.
So you're looking to these basis elements as a operator. You're looking at tensor product of identity operator and a cat.
That's right, because I mean, this works, doesn't matter, but remember we're in finite dimension, so again, this is very concrete, right? That's why it's good finite dimension. This is just the tensor product of dA by dA times dA matrix, right? Which is the identity, times this guy will be tensor product, right? dB times 1 matrix, right? So this is just a row vector, right? And this is just a column vector, right? And that's why, you know, these objects, row AB, it lived, right? It was a matrix in dimension dA times dB, right? Times dA times dB. And row A is only in a matrix of dimension dA times dA, right?
So you multiply a matrix by a row.
No, that's right. So once we do the tensor product using, right, this rule that also applies to matrix, this whole thing is a rectangular matrix, which is a rectangular matrix where the number of columns, yeah. So it's a matrix dA, dB times dA, right? So the number of columns is dA times dB. The number of rows is dA. Okay. And this thing here in the middle is a dA times dB times dA times dB matrix, right? So you see reduce the number of dimensions in the end. Right? So just think at this. Whenever you have this, it's just a vector, right? And this is a square matrix, right? But the tensor product still makes sense there. Right? So try, you know, if you're not familiarized with this, you should do some calculations, right? Because that's, I'll give you one concrete to do, and that's also a good exercise. So one example is just to use this rule to show that if we take the partial trace over A of this guy again, this one here, then you should show that you get the maximally mixed states, identity over 2. Okay? So try to do that. Oh, sorry, Baristo, do you have a question? No. Okay, right, okay. Row A? Yeah, so row A is a density matrix on CDA, which means that it's a dA times dA matrix. Right, yeah. Okay, maybe I can go there directly. Good, so I told you about states. Now let's go to have quantum mechanics, right? We need to talk about dynamics, which is like unitary dynamics, and to talk about measurements, right, to get information. So, no, before that, I'm sorry, because that's what I wanted to say. Okay, trace. But now let's look at the reverse operation. Okay, let's start from a mixed state, and I told you the mixed states, they are very useful, but they're not a fundamental object, right? The fundamental objects are pure states. And why that's the case? That's the case because any mixed states on some system A, you can always think of it as actually just a bigger pure state on A and some other system B, which you do not have access over it, and therefore you have to trace out B, and then you get the same density matrix, right? So there is and that's the idea of a purification. Will also be very useful for us later. So how it works with purification? Suppose you have a density matrix row A. I have to change this. Sorry? Yeah, the big chalk's a bit weird for me, but. Oh, it is? Oh, I see. I can try. Okay, thanks. Yeah, I don't know how to hold them, but yeah, I'll try. Right, so the idea is that given a density matrix, okay, for any density matrix on row A, there always exists a bigger, yeah, it's good actually, a bigger quantum state psi on AB, okay, such that, so actually there exists first a vector space, a Hilbert space B, which we can have a bound on the size of it, but I'll let you figure it out, and a state such that this row A, you can think of it as having the quantum state psi on the bigger space and tracing out B. Okay? So in that sense, you can say, okay, this mixed state really just due to our ignorance, right? Actually, it's just a pure state on the bigger quantum system, but we don't have access to all the particles, and therefore, we think it's a mixed state. So what is the idea of this? Well, we just do it directly, right? So row A is a mixed state, and I told you there is always a way of writing as a convex combination of pure states. In particular, there is a canonical one, which is using the eigenvalues. Let lambda I be the eigenvalues. Is a Hamilton matrix, has eigenvalues and eigenstates, and eigenvectors, sorry. And it's positive semi-definite, so the eigenvalues, they are all bigger or equal to 0. Let psi I be the eigenstates. Okay? And now we just build it directly, right? A possible purification is just this. Where this is just a basis for B. This is a basis. Okay, so exercise, check that if you take the partial trace here, you indeed recover row A, okay? And now another thing, which try to think about what is the minimum dimension that you need for B, right? So this is like, I just said there exists a B, and I say psi AB, which is a purification. What is the minimum size dimension of B that you need, right, to be able to have a purification? So think about that, right? And this, I encourage you to do these questions, right, because this will train you, but I'm not going to mark them, you don't have to do anything, but you can also ask me next time if in case you got stuck in all of them, right? But try to check that that's the case, and try to argue, to figure out what is, there is a number here, right? This number here, of course, is the number of base elements that you need for B, and therefore gives the dimension of B. Try to figure out what is the minimum R that you can put here. Okay? Good, so this was states. Let's look at dynamics. So of course, okay, dynamics, again, the fundamental thing, what it is just Schrodinger equation, right? But Schrodinger equation is a differential equation, right? So I refuse to write it here. I want to write everything in terms of matrices. So I'm just going to write the version where it's just unitary, right? So what is the dynamics? It's just, every dynamics corresponds to a unitary. So we just map psi, maybe psi at 0. He maps it to psi at t. And the way to do that is to apply a unitary matrix. Let's call UT at psi 0, right? Okay. Just in case you want to make you happy, right? So what is this? Just time order, but we're never going to use it, right? But it's time order of, right? It's just what Schrodinger equation tells us, right? So we have a Hamiltonian, right? Right, it's this object, but what concerns us here is that this is unitary, meaning that u dagger u equals u dagger equals identity, right? And particle is reversible, right? You can reverse it. You can apply u dagger, you go back to the same state. Okay? Great. But now you say, okay, now we talk about mixed states. What happened to mixed states, right? Well, pretty much the same if it's really unitary dynamics, right? So if you have some rho of t, how you evolve it from rho 0? Well, you just conjugate by u now, right? So you just do this, right? But actually now you can do something more. And we are going to use these kind of operations. They are useful for us. So what you can do, for example, is you can have your quantum particle. There you want to do some, apply some operation to it. Then you add some other particle, some ancilla particle. You apply some unitary dynamics. You have some Hamiltonian there on the composite system. You apply it for a while, and then you trace out this extra particle, right? And then say, okay, what is the effective dynamics on your system? And then you cannot describe this by unitary dynamics anymore. Okay, so there is also S. This is indeed the fundamental thing in quantum mechanics. You always think of this way, but again, in some larger system, right? And if you just want a description in terms of A only, not involving B, there is a different class of objects, and that's also good for us. So that's what we call quantum operation. So here we are interested in dynamics from density matrices to density matrices, and the most general we can do in quantum mechanics. So we can say rho t now gets mapped by some lambda sub t applied to rho 0. Okay, so that's now a linear map. Lambda t is a linear map on density matrices. And what is the most general form? So this lambda is a quantum operation. And what I mean by a quantum operation is something that you can implement in quantum mechanics, okay? A valid quantum evolution, if and only if lambda is what we call a trace preserving completely positive map, okay? So what is this? So trace preserving completely positive. So what we want is, okay, so let's just think about it like, forget about that it should come from some unitary dynamics, but let's just think about what we want, right? So we have a density matrix, we apply some operation to it, it should map against a density matrix, right? It would be weird if it didn't. So indeed, we want that lambda applied to rho, and this is a density matrix if what? If it's positive semi-definite for all rho, right? And if that's the case, right? For all rho again. So this is what we call a trace preserving operation. Okay, so the trace is preserved. So the trace of rho was 1 before, of course, the density matrix. After lambda is 1 again. This is what we call, comes from this, positivity constraint, right? We want that if it was a density matrix before, again, it's a density matrix afterwards, right? So it has to be a positive semi-definite matrix again. All eigenvalues bigger or equal than 0. But this is not enough, actually. We are missing something here. And what we're missing, again, is composite systems, right? So in quantum mechanics, you can apply this operation just to, you can have a system of 2 particles, for example, or more, and apply this quantum operation just to one of them. And of course, we still want the total density matrix of the 2 particles to be a quantum state again, right? To be positive. So actually, what we have to require here is that I'm just going to erase it and write it. Right? So this is what we call positivity. What is completely positivity is this. Now we have lambda, but we apply lambda just to part of the system and apply identity to the other parts. And now we have some rho AB, and this again has to be positive for all rho AB now. On the okay? So this is like the bare minimum, right? So we just want that it maps density matrices to density matrices, even if you act on part of the system, that makes sense. It turns out that these 2 operations are also enough for this operation to be implemented in quantum mechanics, okay? So, and that's because of the following results. Um,
To apply this operator to the density matrix, it's just a matrix multiplication with finite dimensions.
no, this is a linear map. So think about a way to think about it. I'm going to write explicit now, but a way to think about this is that okay, of course this is a matrix, but it should it's a linear map. It should satisfy the relations of linear maps, right? So well, or let me say explicitly. Think of this as a vector now, right? So this is a density, right? This guy is a vector space as well, right? So you can see this as a vector, and that there's just a matrix on this vector space. Right? But of course, if you write this as a matrix that we are doing that, then this has a different form. Let me write it. So given lambda, given a quantum operation lambda, two things are true. So one is your question. You can always write this in the following form. There exist matrices. They are really matrices now, MK, right, okay, and MK dagger. These are called Krauss operators. And then this is the most general one, but this doesn't put the trace preserving condition yet. So these MKs, they have to satisfy this. Okay? So this is one claim. Anything satisfying that can be written in this form. I won't show you. I don't have time, and maybe it's too much for you. Well, you can try to work out yourself, but maybe it's a bit hard. But what is not hard is to show, and this you should try to do, I think, is to verify that if an operation has this form, if lambda has this form, then it satisfies these two properties, okay? So that's not difficult, and I will ask you to check it. And second, and this is the most operation, this gives a meaning to this. There always exists a unitary U from A and B prime to A and E, okay, such that lambda x can be written in the following form. So we have our quantum particle, oh sorry, this should be x. So we have our quantum particle, like this would be some density matrix, where we want to apply the operation. Then we add another quantum system, this is what we call B prime, in some uncorrelated states, and this can be just any pure state you want, but for example, it can be the zero state there, the first element of some basis there. Then we do some joint quantum operation, so this is just unitary dynamics, right? So this U dagger. This is unitary dynamics there. So we couple the two systems. And this unitary dynamics, we can just relabel things, right? So it maps A, B prime to yeah, but that's, okay, because what can happen here is that the output doesn't have to be A, right? The output can be A prime, right? You can change the dimension, right? This is allowed here, because you can do partial trace, right? So then you apply some unitary dynamics here, you relabel the two spaces the way you want, you trace out, you ignore some of degrees of freedom, and then you get your lambda, okay? So again, it's just, you can say, well, okay, that's great. It's just unitary dynamics again, right? Up to adding some ancilla and throwing away it in the end, right? So that's why, you know, they are useful, but they are not more fundamental than unitary dynamics. Right, so this is just, maybe here. Sometimes I will use this notation, but let me, maybe right here, and who is watching online will not know it. It's our secret, but this I mean this. I mean, is a here, you know, is a. So it's a linear, is a unitary, right? That maps, you know, it acts. Right. So let me write it, then I'll explain more. So these are just vector spaces, right? A prime, each one of them labels a vector space, and we have the promise that they're isomorphic. Okay, so they have the same dimension. So we can have a unitary between them, right? But these are just give you label, right? So we're interested in some dynamics acting on A, only on the system A. I add some ancilla, which lives in this other vector space. So for example, this could be a qubit, and this could be a qubit, right? So for a specific example, so we could have C2 here, and then we add a C4 here, right? But then the output will be 2 qubits, right? So that's fine. We can, well, wait. No, that's not fine. So we want to have, for example, let me see, maybe 4 and 3 here, and then we change, yeah. For example, right? So that means that the input state of our quantum operation is a 4-dimensional quantum system. I add ancilla of a 3-dimensional quantum system. I do some unitary dynamics, so that again, right, the composite system is a 12-dimensional quantum system, but now I can break them in any way I want, right? So I interpret that as a quantum system now of a qubit in a 4-dimensional quantum system, and I will trace out this guy, and the output is a 3-dimensional quantum system, right? So that's an example. So that's what, and sometimes I just ignore the Hilbert space and I just denote by that. Okay, so these are just labels denoting each one of the Hilbert spaces that we use here. Yes. Yeah, that's what I mean. They have to be isomorphic. So basically, the product of the dimensions have to match, right? But apart from that, yeah, you can break any way you want, right? Because here, physically, here is pretty clear what you do, right? So here, suppose you do whatever unitary you want here, and then you just swap the two systems, right? You physically swap the two, right? And then you implement this, right? Okay. Okay, finally measurement, right? So measurement, by given a measurement, again, the most fundamental is projective measurement, right? So we just associate to the measurement some set of projectors, pk. They define the measurement, and they are projectors, so they are Hermitian. They square to themselves, and they are resolution of the identity. And then the probability of measuring k in some quantum states equals to trace rho pk, right? And the post-measurement states rho sub k, that's equal to this guy, okay? So Born's rule, right? And the post-measurement state, we just is this power of quantum mechanics, right, which breaks the linearity. Again, we can have a more general kind of measurements. This we call POVMs, right? So they are more general. But again, we can always think of them as a measurement that we get by adding ancilla, performing a projection measurement on the joint states, and looking at the effects at only our particle, not the ancilla. And I will maybe introduce them later because I think it's getting. We might not need them anyway, but I'm just mentioning the same thing that we do with operations, we can do with measurements too, but let's just leave to that. Okay, so, and let's do that because I promised to Burak that I would teach you one thing that I haven't yet, so I have to do it. So let's go back to entanglement now. Okay, so now let's study entanglement. Pure states. We will finish that last time, but for now, I just want to I'll start telling you. So, right, so we have, let me see what I can tell you now. So again, entanglement is about these correlations between the quantum systems, right? And we're going to see that in more detail later, how we get to operation, what we call operation interpretation of entanglement. So like a meaningful interpretation of entanglement, not related to math. So just related to this, like, we want to understand correlations which can only be created by some quantum interaction which are genuinely quantum and which cannot be described by like classical communication, right? Or by classical shared randomness, by classical correlations. And there is an operational way of doing that, and that's using what we call this LOCC paradigm, local quantum operations in classical communication. But I will tell you this last time. But now, for now, just to justify this definition I'm going to make, let's just use it as a bare minimum of entanglement. Okay, so suppose you have an entangled state, psi AB, of two particles, and this state ought to, entanglement should be about the correlations between this AB, right? But now suppose we implement a unitary U on AB, which is just a unitary on A, and we do nothing on B. Okay, we just implement a reversible transformation on A. And then we get some other state phi, AB, which is this guy. And now I ask you, what happens to the entanglement of AB if you do this local unitary? What do you think will happen?
Same.
Has to be the same, right? Yeah. Why? Because I even haven't told you how to, I just told you what entanglement is, but I haven't told you how to quantify it or anything, right? So who has a good argument? Just from what you know, which I know it's a bit too much to ask because I haven't told you anything. Who has a guess? So think about it. So entanglement is about correlations, right? So whatever you do with the, if you do some local operation, right, you cannot create these correlations, right? But you could destroy the correlations, right? So maybe you apply this UA and you destroy a little bit the correlation between A and B. But that cannot happen, right? And why that cannot happen? Because this is reversible, right? So, you know, if you destroy it a little bit, well, we can apply the reverse operation here and get back psi, right? But then we have created it a little bit from some local operation, which doesn't make sense, right? So because it's reversible and should not at least create it, it cannot destroy either, right? So entanglement, whatever it is, and we see more next time, has to be invariant on this class of operations, right? So that's one observation, entanglement. Has to be invariant under UA VB, right? Under local unitaries. Okay. And now that's good because suppose we have a quantum state psi, and all we care about is entanglement. We don't care about any other property. Then there is a normal form that we can put the states. Okay, so and that's what we call the Shimmy decomposition. So, given psi b, there exists numbers lambda I. They are all bigger and or equal than 0, and local basis IB. So local basis for the A and B vector spaces, such that we can write psi as sum over I is square root lambda I IA tensor IB. Okay? So note, these are not the computational basis. The result is just saying that given any psi, I can find some positive numbers, real numbers, and some bases. I have to find the particular basis such that basically can be written in this form. And why that's special? Well, because first, remember, the general decomposition, right, had a double sum. We had to sum over local base on A and B. Now here's the same, I. They're correlated, right, there. And these lambda i's, they are all positive, right? They didn't have to be. So this is called the Schmidt eigenbasis. These are called the Schmidt eigenvalues. And why that's the case? Well, that follows from the singular value decomposition, right? So, I'll give you, yeah, this will be the last thing you have to do for tomorrow. So I'll give you some ingredients. So the first is, let me introduce a class of states we're going to use the next time too. They are called maximally entangled states. And for every dimension, there is one. In the dimensions, maybe I can put D here. They're defined like that. They're just perfectly correlated, right? It's just an extension or a generalization of that state I wrote before. And now there is an isomorphism that is very useful. So maybe states operator isomorphism, which is the first thing you have to prove that it works. What it says that given psi, okay, every psi AB that you want can be written as identity on a matrix X applied to this maximally entangled state. Okay? So I ask you to show this. Given any psi, find a matrix X for which this identity holds. Okay, and that's you show that that can always be done. But then once we have this realization, right? So we're going to see later that these pure states, we understand entanglement very well there. Okay, we have a lot of theory there. But once you go to more particles, or once you go to mixed states, everything fails, becomes very complicated. In the worst case, at least. And then, of course, we have to do more approximations and so on in particular cases. And that's one of the reasons, really, because of this isomorphism, everything about entanglement of two particles, pure states, is about matrices, right? And then linear algebra there is great, right? So we understand linear algebra very well, right? Or matrix algebra more, right? So there is singular values, there is everything. But once we go to more, then we have tensors here, right? And that we don't know much about tensors, right? They are much more complicated objects than matrices. So that's one explanation for some of the stuff we're going to see later. But just to finish the class, so I will ask you to try to show that this is the case using this as the first ingredient, and the second one is singular value decomposition, right? Probably you saw it before, but let me just tell you what it is. So given some matrix X, it can be a rectangular matrix. You can always, before that, so it'll be three properties actually. So this is one. The second one is a very useful property of maximally entangled states. Again, I have to check if you apply X to half of a maximally entangled state. That's the same thing as applying X transpose to the other half. Okay? So they have this symmetry. Again, it's just a computation, you can check it. And finally, just SVD, which, right, it's just a statement about matrices. Given any matrix, you can always write it as unitary to the left, a diagonal matrix, and another unitary to the right, okay? And even if it is rectangular, you can do that, but then some of the elements here in the diagonal, they will be 0, right? And moreover, of course now, right, so, you know, how you get these guys? So you get from the eigenvalue decompositions of x dagger and x dagger x, right? So this is equal to u d square u dagger, and this other one is equal to v dagger v. Okay, so that's how you do the singular value decomposition. You get x, can be anything. You compute x dagger and x dagger x. You do the eigenvalue decomposition. You get these matrices. This is a positive system definite matrix. So the eigenvalues, they are always, right, bigger than 0. So you can take the square root of this and define the singular values. Okay, and now just give you a tip. This guy will tell you the Schmidt eigenbasis of B. This will tell you the Schmidt eigenbasis of A, and this will tell you the Schmidt eigenvalues. Okay, so I ask you to figure this all out using these 3 tips. So I probably was very slow for some of you, but I hope for some of others it was good. So next time we get to more interesting things. But before I end, is there any question? Yes. No, they do not have to have. No. Yeah. So this works in general, even if they don't have the same dimension. No, I mean it might be. It might be that. Okay. So let me specify more clear. So okay. So so this goes. Let me see how I say that. So. This forms a basis, but not all elements of the basis have to appear here. It can be just a subset of a basis for B, for example, and the same thing for A. Okay, so, but this works in any, even when they don't have the same dimension, and that's exactly because singular value decomposition works for some rectangular matrix too, right? So you can check it out. Yes. We didn't, but we can add them. Yeah. So.
So there will be a 30-minute coffee break now, and then we have Burak's lecture.
I would save the last 5-10 minutes for questions.
Sure.
Sure. If there are
So you say like speak for an hour, 20 minutes, and then 10 minutes question. Sure. Yeah. We can do that from tomorrow, but yeah, we can also continue today for. Yeah. Sure, sure.
Sometimes entanglement theory is like a mathematical tool that you use to apply to these other areas, and that's the way you do it, or is there actually a physics associated with entanglement?
Yeah, there is, but we haven't got to it yet. But like, well, I mean, it depends what you call physics, right? But it's a physics in the way that's.
Are there competing models of entanglement? Usually when we have physics and we want to we have competing models and we see which is better, which is.
There is in a sense, but not as interesting as in other areas of physics. There is like many, entanglement is like a complicated thing. So there are, for example, if you want to say how much entanglement there is in the states, there is many ways of doing that, and it's not clear what is the right one. But I guess your question is more, on one hand I would say it's more as a tool. So using this as a tool, you can understand better the physics that you couldn't before. So for example, you can understand better quantum error correction, and then one application, you can understand better some features of ADS-CFT that's they seems mysterious before, and then so if you just see this as a quantum error correcting code, that's very clear now. But you have to understand entanglement for that, right? But there is also, I think, a more fundamental thing, which is, you know, correlation is something very fundamental in physics, right? We understand correlations in two systems can be in classical mechanics or in quantum mechanics, but it's not clear yet. But next time we're going to see how entanglement leads to a view of correlations which is fundamentally different from what happens in classical mechanics. So I think that's a feature of quantum mechanics which is very peculiar, which is worth studying and understanding better. There is, because, well, not, probably not in this course because I'm abstracting in a way, but the point where it enters is just that because of the coherence, okay, whenever we have macroscopic systems, we just don't know a way of maintaining the entanglement there. So we must go to the microscopic level to be able to see that. But that's not maybe something, we don't know yet if it's fundamental or not. It's just that when you have, it's just the entanglement is very fragile. Quantum systems like to interact with the environments, right? And as we're going to see, this interaction with the environment degrades the entanglements. Right? So, but we don't know if it's a fundamental thing or not. It could be the H bar actually doesn't matter. As long as we had money enough to isolate it enough, we could build a very big system which would be highly entangled. I doubt it, right? We're not there yet. But we don't understand yet this transition of quantum and classical. Right? Okay. Any other question? Yes. Well, yeah, because I haven't told you, wait for next time, but let me tell you one particular example, okay? Suppose psi was a pure state, was a non-entangled state, just a product state. If you apply a unitary of this form, you get a product state again, right? So it's not entangled again, right? So you definitely cannot create entanglement by this kind of operations, right? When I tell you even something more, you cannot, next time we're going to see how to quantify entanglement, to tell how much entanglement there is in a state. And I'm telling you that by these operations, you cannot change the amount of entanglement. The amount has to be the same as well. But
so if you apply it to a maximally entangled state, you will obtain a maximally entangled state.
You will. Although, yeah, I'm calling this maximally entangled state, but that's not the only maximally entangled state. Yeah, but, yeah. Okay.
So if there are no more questions, we thank the speaker.
Thank you.
There's a 30 minutes coffee break.
Não, mas vai ter que... Não,